Tonight, we're going to follow a spacecraft into the dark. Not a movie, not a simulation, an actual piece of human-built machinery launched in 1972 that crossed every boundary we knew how to measure, and then started doing something it was never supposed to do. Its name was Pioneer 10. It was smaller than a Volkswagen Beetle. It carried less computing power than a digital watch sitting on your wrist right now. And when scientists finally stopped receiving signals from it, the data it had been quietly transmitting for 3 decades had already shattered assumptions about the edge of our solar system. By the end of tonight, you're going to understand why an aging probe drifting toward a star it will never reach became one of the most disturbing scientific puzzles of the 20th century. You're going to learn what the heliosphere actually is, why crossing it matters, and what Pioneer 10 sent back from the void that physicists spent 30 years trying to explain away. And you're going to see why the silence that followed its final transmission still echoes through observatories today. Before we go further, if you find these journeys into deep space as compelling as we do, take a moment to like the video or subscribe. It costs nothing, takes a second, and it genuinely helps this channel reach more curious minds who want to think about the universe at this depth. Now, let's begin. On March 2nd, 1972, an Atlas Centaur rocket lifted off from Cape Kennedy, carrying something humanity had never attempted before. Every spacecraft launched up to that moment had been bound by an invisible leash. Mariners orbited the sun in tight loops near Earth. Apollos went to the moon and came back. Even the most ambitious probes stayed comfortably within the inner solar system, where the sun's warmth was familiar and the stars stayed in roughly the same patterns. But Pioneer 10 was different. Its mission was not to orbit anything. Its mission was to leave, to cross the asteroid belt, a region that NASA scientists genuinely feared might destroy any spacecraft attempting to traverse it. To fly past Jupiter, the largest and most dangerous planet in our system, with a radiation belt powerful enough to fry electronics in minutes. And then, if it survived all of that, to keep going, forever, outward, toward a star called Aldebaran in the constellation Taurus, a star Pioneer 10 will not reach for another 2 million years. Think about that timeline for a moment. 2 million years. The entirety of recorded human history is roughly 5,000 years. Agriculture itself is only about 12,000 years old. Modern humans have existed in our current anatomical form for maybe 300,000 years. Pioneer 10's journey to its first stellar target is more than 6 times longer than the entire existence of our species. And yet, this tiny machine, designed in the 1960s with technology that engineers today would consider almost laughably primitive, is the first object we ever launched on such a journey. It's our first ambassador to the rest of the galaxy, and bolted to its main antenna support is a gold anodized aluminum plaque, 6 inches by 9 inches, designed by Carl Sagan and Frank Drake and Linda Saltzman Sagan. The plaque shows a man and a woman, the position of our sun relative to 14 pulsars, and a diagram of our solar system. It's a message in a bottle thrown into the cosmic ocean, a message we have no way of recalling. A message that might never be read, or might be read by something we cannot imagine. But the plaque, as famous as it became, is not why we're here tonight. We're here because somewhere out beyond Jupiter, somewhere in the cold, dark, mostly empty space between the planets, Pioneer 10 began to slow down. Not by much. The deceleration was so small that for years no one even noticed it. We're talking about a change in velocity smaller than a billionth of the acceleration you feel from Earth's gravity. To detect it required some of the most precise distance measurements ever made in the history of science. But the deceleration was real. It was persistent. It was directed back toward the sun, as if some invisible force were pulling on the spacecraft, refusing to let it go. And it could not be explained by any known physics. This became known as the Pioneer Anomaly. And for 30 years, it haunted the field of celestial mechanics. Some physicists thought it was evidence that our understanding of gravity itself was incomplete. Others suspected dark matter was somehow involved. A few wondered, quietly, whether something was waiting at the edge of the solar system, something we hadn't predicted and couldn't see, that was reaching out and tugging on our first envoy into the dark. The anomaly was real enough to launch an entire research program. real enough to produce dozens of academic papers, international conferences, and proposals for new spacecraft missions specifically designed to test it. And the resolution, when it finally came in 2012, was both more mundane and stranger than anyone expected. We'll get to that in time. But Pioneer 10's deceleration was only one of the mysteries. As the probe pushed deeper into the outer solar system, it began transmitting data about a region of space we had never directly sampled. The heliosphere, the vast magnetic bubble created by the sun's solar wind, was thought to be relatively stable, relatively well understood, relatively boring. Pioneer 10 discovered that almost everything we believed about its outer reaches was wrong. The bubble was being battered by forces from interstellar space we had not predicted. Its boundary, the heliopause, was not a smooth shell, but a turbulent, churning frontier where the solar wind crashed into the interstellar medium in ways that made no theoretical sense. And the cosmic ray, flux beyond a certain distance, behaved in ways that contradicted our most confident models. For 3 decades, this small spacecraft kept whispering data back to Earth. Its signal grew fainter and fainter, until receiving it required some of the most sensitive radio dishes ever built, listening for hours just to extract a few bits of information. By the late 1990s, its plutonium power source was running down. Its instruments were failing one by one. And then, on January 23, 2003, the Deep Space Network received its last detectable signal. Pioneer 10 was, at that moment, approximately 7.6 billion miles from Earth. After 31 years of continuous communication, after surviving radiation that should have killed it, after sending back data that overturned multiple scientific models, our first interstellar ambassador went silent. And it kept moving. Even as I am speaking to you now, Pioneer 10 is still out there, drifting deeper into the dark, carrying its plaque and its unsolved mysteries. But what it sent back before it vanished, that's the real story. That's what we're going to unpack tonight, piece by piece, mystery by mystery. Because what Pioneer 10 told us about the boundary of our solar system, about gravity, about the silence on the other side of the heliosphere, is genuinely, scientifically, undeniably terrifying. To understand why Pioneer 10 mattered so much, you have to understand the world that built it. The late 1960s in America was a strange and electric time for science. The Apollo program was consuming nearly 4% of the entire federal budget. The Cold War was at its most paranoid. Vietnam was burning. And inside a relatively quiet cluster of buildings at NASA's Ames Research Center in Mountain View, California, a small group of engineers was working on something almost no one in the public knew about. While the country watched astronauts plant flags on lunar regolith, these engineers were sketching designs for a machine that would never come back. A machine that would, if everything went right, leave the solar system entirely and become the first human-made object to enter interstellar space. The program was called Pioneer, and it already had a long and bruised history. The first Pioneer missions, launched between 1958 and 1960, were almost entirely failures. Pioneer 0 exploded 77 seconds after launch. Pioneer 1 came up short of the moon. Pioneer 2 re-entered the atmosphere and broke apart. Pioneer 3 fell back to Earth. The early Pioneer program was the kind of catastrophe-by-catastrophe learning process that defined the dawn of the space age. Each failure taught engineers something new about rockets, about radiation, about how machines behave in environments humans had never built for. By the mid-1960s, the Pioneer program had matured. Pioneers 6 through 9 became long-lived solar monitoring spacecraft, drifting in orbits around the sun, sending back data on solar wind and cosmic rays for years on end. They proved that NASA could build machines that lasted. They proved that small probes, far cheaper than the Apollo-class missions grabbing headlines, could do real, lasting science. And they laid the groundwork for what came next. In 1969, NASA officially approved 2 new Pioneer missions, Pioneer F and Pioneer G, which would later be renamed Pioneer 10 and Pioneer 11 once they reached orbit. The mission was breathtaking in its ambition. These probes would be the first spacecraft ever to attempt crossing the asteroid belt, the first to encounter Jupiter, and ultimately the first to leave the solar system. They would have to operate for decades, in environments no human-made object had ever experienced, with no possibility of repair, no opportunity for upgrades, and signals that would take longer and longer to reach Earth as they receded into the dark. The challenge was assigned primarily to NASA Ames, with TRW Systems in Redondo Beach contracted to actually build the spacecraft. The lead project scientist was a soft-spoken engineer named Charles Hall, who would devote a significant portion of his career to this single mission. The engineering problems were genuinely terrifying. Sunlight at Jupiter's distance is only about 4% as strong as it is at Earth, which meant solar panels were useless for power. Pioneer 10 would have to carry its own power source. The solution was a set of 4 radioisotope thermoelectric generators, called RTGs, mounted on long booms extending away from the main spacecraft body. Each RTG contained a small amount of plutonium-238, a radioactive isotope that decays into uranium-234, releasing heat in the process. That heat was converted directly into electricity by thermocouples. At launch, the RTGs produced about 155 watts of power, roughly the same as a single incandescent light bulb. By the time Pioneer 10 was approaching the outer edge of the solar system, that output had dropped to less than 65 watts. Everything the spacecraft did, every measurement, every transmission, every internal heater, every instrument, ran on less power than a household lamp. Then there was the asteroid belt. In the late 1960s, no spacecraft had ever attempted to cross it. The belt, lying between the orbits of Mars and Jupiter, contained an unknown number of rocks ranging from grains of dust to bodies hundreds of miles across. NASA scientists genuinely did not know whether a spacecraft could survive the passage. Some models predicted Pioneer 10 had a real chance of being struck and destroyed before it ever reached Jupiter. Other models suggested the belt was so vast and so empty that the probability of impact was vanishingly small. Nobody knew which model was correct. The only way to find out was to send a probe and see whether it came out the other side. In a very real sense, Pioneer 10 was a test pilot. Its survival or its destruction would write the textbook future missions would rely on. The third great problem was Jupiter itself. The largest planet in the solar system possessed a magnetic field of staggering intensity and a radiation environment that engineers feared might fry the spacecraft's electronics outright. Pioneer 10 would have to fly within 81,000 miles of Jupiter's cloud tops, deep into a radiation belt that nothing humans had built was certified to survive. Every chip on the spacecraft had to be hardened against an environment we had never directly measured. The engineers were, in effect, making educated guesses about how much shielding to install. Too little, and the probe would die before it could even take its first close-up images. Too much and the added weight might make the launch impossible. The balance they struck was an act of engineering courage as much as calculation. And then there was the plaque. As designs were being finalized in 1971, the journalist Eric Burgess realized something extraordinary about the mission. Pioneer 10 was not just going to Jupiter. It was leaving the solar system permanently. It would drift through the galaxy essentially forever, almost certainly outlasting every human civilization, every monument, every record we have ever produced. Burgess approached Carl Sagan with an idea. What if the spacecraft carried a message? A message intended not for humans, but for whatever might one day find it in the deep dark between stars. Sagan and Frank Drake designed the now famous plaque in a matter of weeks. The man and the woman, naked and rendered as scientifically as possible, stood beside a schematic of the solar system showing Pioneer 10's trajectory. A diagram of 14 pulsars marked our cosmic address. A hyperfine transition of hydrogen provided the universal unit of length. Linda Saltzman Sagan etched the figures by hand. The plaque was attached to one of the antenna support struts, where it would be partially shielded from erosion by interstellar dust. It was an act of profound optimism in the middle of a fundamentally lonely mission. By early 1972, the spacecraft was complete. Pioneer 10 weighed 570 pounds, stood about 10 feet tall with its dish antenna fully deployed, and carried 11 scientific instruments designed to measure magnetic fields, cosmic rays, charged particles, and the structure of space itself far from the sun. It was, by modern standards, a delicate, almost fragile thing, but it was also the most ambitious machine humans had ever built. On March 2, 1972, sitting on top of an Atlas Centaur rocket and a kick stage of solid-fuel boosters, Pioneer 10 was lifted into the sky and accelerated to the fastest velocity any artificial object had ever achieved. Within hours, it was past the orbit of the Moon. Within months, it was approaching the asteroid belt. Nobody on the ground knew what would happen next, but the doors had been kicked open, and the dark on the other side was waiting. In the months leading up to Pioneer 10's launch, the scientific community held a remarkably tidy picture of what lay between the planets. It was a picture built almost entirely from theory, from Earth-based observations, and from a handful of probes that had ventured no farther than Mars. By the standards of the 1970s, it was confident, mathematically elegant, and very nearly wrong about almost everything that mattered. To appreciate just how much Pioneer 10 was about to overturn, you have to understand what the textbooks of 1971 said about the space between the sun and the stars. And you have to understand how completely those textbooks were going to be rewritten in the decades that followed. The dominant framework had been built primarily by an astrophysicist at the University of Chicago named Eugene Parker. In 1958, while still a young researcher, Parker published a paper proposing something so strange that the established journals initially refused to print it. He argued that the sun was not surrounded by quiet vacuum, but by a continuous, supersonic outflow of charged particles streaming outward in all directions. He called this flow the solar wind. The reviewers thought he was wrong. One senior physicist told him the idea was nonsense, that the sun's atmosphere could not be losing mass at the rates Parker was suggesting. The paper was rejected, appealed, and only published after the editor of the Astrophysical Journal personally overrode his own reviewers. 3 years later, the Soviet Luna 1 probe and then NASA's Mariner 2 detected the solar wind directly, exactly as Parker had described. Within a few years, the solar wind became one of the foundational concepts of modern heliophysics. Parker had been right, and his framework reshaped how everyone thought about interplanetary space. If the sun was constantly blowing out a wind of charged particles, then that wind had to go somewhere. It could not flow outward forever, because eventually it had to encounter the interstellar medium, the thin, cold, irregular soup of hydrogen and helium and dust that filled the space between the stars. Somewhere out there, in the dark beyond the planets, the solar wind would slow down, then stop, then push against the interstellar gas like a bubble pushing against water. That bubble had a name. It was called the heliosphere. And its outer boundary, the place where the solar wind's outward pressure finally balanced the inward pressure of the interstellar medium, was called the heliopause. In the late 1960s and early 1970s, the heliosphere was almost entirely a theoretical object. Nobody had ever directly measured its outer regions. Nobody knew exactly where the heliopause lay. Calculations based on Parker's solar wind model placed it somewhere between 50 and 150 astronomical units from the Sun, where 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. The uncertainty was enormous. Some models suggested the heliosphere was roughly spherical. Others predicted it would be flattened and stretched into a long tail by the Sun's motion through the galaxy, like a comet's tail trailing behind a moving body. There were models with a smooth, well-defined boundary. There were models with turbulent, churning regions where the solar wind crashed into the interstellar gas in unpredictable ways. And because nobody had ever measured any of it directly, nobody could choose between them. What scientists believed they could be confident about was a kind of layered, predictable geometry. The Sun, they said, would be surrounded by the supersonic solar wind out to a certain distance. Beyond that, the solar wind would slow abruptly at a feature called the termination shock, decelerating from supersonic speeds down to subsonic flow. Past the termination shock would lie a region called the Heliosphere, where the slowed solar wind would pile up and eventually merge with the interstellar medium. The outer boundary of the Heliosphere was the heliopause itself, the true edge of the Sun's domain. Beyond the heliopause lay interstellar space, the unfiltered, unsorted, ancient stuff of the galaxy. And there was, in principle, a third feature called the bow shock, where the interstellar medium itself would pile up against the heliosphere's leading edge as the Sun plowed through the galaxy. It was an orderly, well-reasoned model. It was the kind of model physicists liked, because it had clean predictions and clean boundaries. Pioneer 10 was about to demonstrate that the actual region of space the model described was nothing like the prediction. There were other beliefs about the outer solar system that came packaged with this framework. Scientists assumed that cosmic rays, the high-energy particles streaming through the galaxy from supernovas and other violent events, would be relatively well shielded inside the heliosphere. The solar wind, by carrying the Sun's magnetic field outward, was thought to deflect most of the lower-energy cosmic rays before they could reach the inner planets. This shielding effect, called solar modulation, was already known to vary with the Sun's 11-year activity cycle. During solar maximum, when the Sun was most active, fewer cosmic rays reached Earth. During solar minimum, the cosmic ray flux at Earth went up. The framework predicted that as a spacecraft moved outward from the Sun, the cosmic ray flux should increase steadily, reaching a kind of plateau in the outer heliosphere and approaching the true interstellar value only after crossing the heliopause. It was a simple, monotonic prediction. Cosmic rays would rise as Pioneer 10 traveled farther out. Period. There were assumptions about dust as well. The interplanetary medium was believed to contain a thin haze of micrometeoroid particles, fragments of asteroids and comets ground down over billions of years. The density of this dust was thought to fall off rapidly with distance from the Sun, because the source population, mostly asteroids and short-period comets, was concentrated in the inner solar system. By the time a spacecraft reached Jupiter's orbit, the dust density was supposed to be dramatically lower than near Earth. By the time it reached the outer solar system, it should be essentially negligible. This was important for engineering reasons, because micrometeoroid impacts could damage instruments and, over time, erode optical surfaces. The 1971 expectation was that Pioneer 10, once it cleared the asteroid belt, would spend most of its life in a remarkably clean, dust-free environment. And there was a deeper, almost unstated assumption underlying all of this. Gravity in the outer solar system was thought to be perfectly well understood. Newton's law of universal gravitation, modified slightly by Einstein's general relativity for extreme cases, had been tested countless times in the laboratory and against the orbits of every planet from Mercury to Neptune. Mercury's perihelion precession, the slow rotation of its orbit that Newtonian mechanics could not quite explain, had been resolved by Einstein in 1915. Beyond that, gravity in the solar system was considered a closed problem. Once you knew the masses of the Sun and planets, and the position and velocity of any object, you could predict its trajectory with breathtaking precision for centuries into the future. The orbital mechanics teams at the Jet Propulsion Laboratory could plot Pioneer 10's path to Jupiter with errors measured in tens of miles after a journey of hundreds of millions. Gravity, they were certain, would do exactly what gravity always did. The textbooks in 1972 were closed on this question. Every one of these assumptions, the tidy heliosphere, the simple cosmic ray gradient, the dust-free outer void, the closed book on gravity, was about to develop a crack. The first crack in the conventional picture came faster than anyone had expected. Pioneer 10 reached the inner edge of the asteroid belt in July of 1972, only 4 months after launch, and immediately began returning data that puzzled the mission scientists. The micrometeoroid detectors mounted on the spacecraft were designed to register impacts from particles down to 1/10 of a millionth of a gram. Engineers had braced for a substantial increase in dust impacts as the probe pushed deeper into the belt. They had run worst-case simulations in which Pioneer 10 was so peppered with debris that key systems failed before it ever reached Jupiter, What the spacecraft actually reported, however, was almost the opposite. The impact rate inside the asteroid belt was barely distinguishable from the rate outside it. Pioneer 10 sailed through the region almost untouched. The dust was there, but the belt was so unimaginably vast and so unimaginably empty that the probability of any given cubic mile containing anything dangerous was vanishingly small. The asteroid belt, far from being the cosmic minefield mission planners had feared, turned out to be one of the most tranquil regions Pioneer 10 would ever cross. This first surprise was greeted, oddly, with relief rather than alarm. The spacecraft had survived. The mission was on track. Scientists tweaked their dust models, published a few papers, and moved on. But in hindsight, this was the first sign that the theoretical framework guiding the mission was less reliable than anyone had admitted. The asteroid belt had been studied, modeled, observed, and theorized for over a century. Astronomers had calculated impact probabilities from first principles, drawing on every observation of every known asteroid. And the answer they had produced was wrong, not by a small factor, but by orders of magnitude. If the textbooks were that far off about a region inside the solar system, about a region we could actually see, what were they getting wrong about the regions we had never been to? Pioneer 10 reached Jupiter on December 3, 1973, and the encounter delivered the second crack. The spacecraft passed within 81,000 miles of the Jovian cloud tops, plunging through a radiation environment more intense than anything any machine had ever survived. Engineers at NASA Ames watched the telemetry with their hearts in their throats. They had built shielding based on the best available estimates of Jupiter's magnetosphere, but those estimates were themselves built on theory, not measurement. As Pioneer 10 dove toward the planet, its radiation detectors went off the scale, then off the scale of the off-scale settings. The actual radiation flux turned out to be roughly 10,000 times stronger than the flux around Earth. Several instruments registered false signals. The imaging photopolarimeter, the instrument responsible for sending back the famous close-up images of Jupiter, momentarily lost its lock on the planet because of radiation-induced noise. By the time Pioneer 10 emerged from the inner magnetosphere, several of its detectors had absorbed more radiation than they had been certified to withstand. It survived, but it survived by a margin that no engineer would describe as comfortable. And the model of Jupiter's environment that NASA had carried into the encounter, the model painstakingly assembled from years of Earth-based radio observations and theoretical magnetohydrodynamics, was revealed to be substantially wrong. Jupiter was a more violent place than anyone had predicted. This was the second crack. The first had been the unexpected gentleness of the asteroid belt. The second was the unexpected ferocity of Jupiter's radiation. Together, they sent a quiet, uncomfortable message to mission scientists. Our theoretical models, the ones based on the best physics of the early 1970s, were missing important things. Whatever Pioneer 10 was about to find in the outer solar system, where no probe had ever been, where no model had ever been tested against direct measurement, was almost certainly going to surprise us again. But the third crack, the one that would haunt physics for 30 years, did not announce itself with a flash or a dramatic instrument failure. It crept in slowly, almost invisibly, hidden in the routine data that the Deep Space Network collected every time it tracked the spacecraft. To understand how it was discovered, you have to understand how NASA actually keeps track of distant probes. A spacecraft like Pioneer 10 does not broadcast its position. There is no GPS in deep space. Instead, NASA tracks the probe by measuring the Doppler shift of its radio signal. When Pioneer 10 transmits at a certain frequency, that frequency arrives at Earth slightly shifted, depending on how fast the spacecraft is moving relative to us. By analyzing the Doppler shift with extraordinary precision, navigators can calculate the probe's velocity along the line of sight. Combined with the round-trip travel time of the radio signal, this gives them the spacecraft's distance and speed with errors measured in fractions of a meter per second. It is one of the most precise measurements humans routinely perform. In the late 1970s, as Pioneer 10 sailed past the orbit of Saturn and continued outward, a small team of orbital dynamicists at the Jet Propulsion Laboratory began to notice something odd. The Doppler measurements were drifting away from the predicted trajectory, not by much. The discrepancy was so small that for years it could be dismissed as measurement noise or as residual modeling error in the gravitational influences of the outer planets, or as the result of subtle thermal effects on the spacecraft itself. The lead navigator on the project, a soft-spoken physicist named John Anderson, kept finding the same discrepancy in his data. The probe seemed to be accelerating very slightly toward the Sun. The deceleration was roughly 8.74 times 10 to the negative 10th meters per second squared. To put that in context, it would take more than 400 years for a deceleration that weak to slow a car by a single mile per hour. It was, by everyday standards, nothing. But it was a persistent nothing. It was nothing that would not go away. Anderson and his colleagues tried every conventional explanation they could think of. They modeled the gravitational pull of every known body in the solar system. They accounted for radiation pressure from the sun. They considered fuel leaks, subtle attitude control thruster firings, gas escaping from the spacecraft's thermal blankets. One by one, they ruled out the candidates. The discrepancy remained. And as the years rolled on and Pioneer 11, the twin probe launched a year after its sister, began returning the same kind of tracking data, the pattern emerged with disturbing clarity. Both spacecraft were exhibiting the same anomalous deceleration. Both were slowing down by the same tiny, persistent amount. Two independent missions, on different trajectories, were behaving in identical defiance of the gravitational laws that physicists considered fully understood. This was the moment something fundamental began to crack. The asteroid belt being empty was a surprise about astronomy. The radiation belt at Jupiter being intense was a surprise about planetary science. But two spacecraft refusing to follow Newton's laws was a surprise about gravity itself. And gravity, in 1980, was supposed to be one of the most thoroughly understood forces in physics. By the early 1980s, the question had a name: the Pioneer Anomaly. Nobody at JPL was willing to say publicly what they were all beginning to whisper privately. Something out there, in the silence beyond Saturn, was pulling on Pioneer 10. Something the textbooks had not predicted. Something nobody knew how to explain. To appreciate what Anderson's team had stumbled onto, you have to appreciate the staggering precision required to find it in the first place. The Pioneer Anomaly was not a thing you could see in raw data. It was not a flashing red light on a console or a deviation visible to the naked eye. It was a whisper hidden beneath layers of noise, a deviation smaller than 1 part in 10 billion, extracted from radio signals so faint that catching them at all bordered on the impossible. The technology that made the discovery possible was, in many ways, more remarkable than the discovery itself. To understand what Pioneer 10 was telling us, you first have to understand how we were able to hear it speaking at all. The listening apparatus is called the Deep Space Network, and it remains, half a century after Pioneer 10 launched, one of the most sophisticated and underappreciated pieces of infrastructure humanity has ever built. The network consists of 3 primary tracking complexes, deliberately spaced 120 degrees apart around the Earth, so that at any given moment, at least one of them has a clear view of any spacecraft in deep space. One complex sits in the Mojave Desert at Goldstone, California. Another is buried in the rolling hills near Madrid, Spain. The third stands in the dry Australian bush outside Canberra. As the Earth rotates, the network hands off tracking duties from one site to the next, ensuring that no signal from a distant probe is ever lost to the geometry of our own planet. Each complex hosts a flagship, antenna 70 meters across, a parabolic dish nearly the size of a football field, capable of detecting signals so faint that the total energy collected from a transmitting spacecraft over decades of tracking is less than the kinetic energy of a single snowflake falling from a roof. The math of this is genuinely difficult to grasp. By the time Pioneer 10 was beyond the orbit of Saturn, its 8-watt radio transmitter was broadcasting a signal that, by the time it reached Earth, had been spread out across billions of cubic miles of space. The signal arriving at a deep space network dish was on the order of 10 to the negative 21st watts. To put that number in human terms, the entire amount of energy received from Pioneer 10 over the course of an hour-long tracking pass was less than the energy required to lift a grain of sand by a millimeter. The receivers that pulled this signal out of cosmic background noise relied on maser amplifiers cooled to a few degrees above absolute zero, devices so sensitive that the warmth of a passing bird could overwhelm the data. Engineers built shielded enclosures, refrigerated electronics, and signal processing chains of almost paranoid complexity, all to extract a single, persistent tone from the static of the universe. But the signal alone was not enough. To measure the anomaly, Anderson's team needed to know how the signal's frequency was changing over time, and they needed to know it with breathtaking accuracy. This required clocks, not ordinary clocks. The Deep Space Network is built around hydrogen maser atomic clocks, instruments that exploit the natural oscillation of hydrogen atoms to maintain a frequency reference stable to roughly 1 part in 10 to the 15th power. A hydrogen maser would drift by less than a single second over 30 million years. The Doppler tracking technique works by uplinking a signal at a precisely known frequency from one of these clocks on Earth, having the spacecraft receive that signal and transmit it back at a slightly shifted frequency, and then comparing the received frequency to the original. The difference, due to the relative motion between the spacecraft and Earth, encodes the probe's line-of-sight velocity. By integrating that velocity over time, navigators could determine the probe's position. And by comparing the measured position to the predicted position from their gravitational models, they could detect any unexplained motion. The software that did this comparison was its own marvel. Developed and refined at the Jet Propulsion Laboratory over decades, the Orbit Determination Program, known internally as ODP, accepted millions of Doppler measurements and processed them through a model of the solar system that accounted for the gravitational influence of every known body, the relativistic effects predicted by Einstein's general relativity, the pressure of sunlight on the spacecraft, the subtle drag of the interplanetary medium, the slight changes in Earth's rotation, the deformation of Earth's surface due to ocean tides, and dozens of other corrections most people have never heard of. The program had to know where the Earth was at every instant, where the Sun was, where Jupiter was, where Saturn was. It had to model the radio waves themselves as they passed through the solar corona, where ionized plasma could subtly alter their propagation. It had to account for the troposphere and ionosphere on Earth, which delayed signals depending on weather and solar activity. Every one of these corrections had been tested, refined, and trusted for decades. And after all of them were applied, after every known effect was modeled and subtracted, what remained, what stubbornly, persistently remained, was a tiny residual drift toward the Sun. Anderson and his colleagues spent years inside that residual. They were not theoretical physicists looking for exotic explanations. They were navigators, engineers, mathematicians whose job was to make spacecraft go where they were supposed to go. When something in the data refused to fit, their instinct was to assume the model was incomplete, not the physics. They added more corrections. They refined the gravitational influence of the Kuiper belt. They considered the possibility that solar radiation pressure was being computed slightly wrong. They modeled potential gas leaks from the spacecraft's propulsion system, even though the propulsion system had been used only sparingly. They considered thermal radiation from the radioisotope generators, the tiny push that the heat radiating away from the RTGs could exert on the spacecraft. By the early 1990s, when Anderson was joined by physicist Michael Martin Niato, and later by Slava Turyshev, the analysis had become an obsession. The team published a major paper in 1998, then a more detailed follow-up in 2002, presenting the anomaly to the broader physics community for serious consideration. They did not claim to have discovered new physics. They claimed only this: two spacecraft, tracked with the most precise instruments humans had ever built, were doing something that none of the known forces of nature appeared to explain. The reaction was immediate and intense. Theoretical physicists around the world began constructing explanations. Some proposed modifications to general relativity. Others invoked exotic forms of dark matter. A few suggested that the anomaly might be evidence for entirely new fundamental forces operating at large distances. The Pioneer Anomaly became a touchstone, a piece of clean, well-documented data that did not fit, and that simple non-fit became one of the more provocative open problems in late 20th century physics. None of this would have been possible without the Deep Space Network, the hydrogen masers, the orbit determination software, and the patient, decade-long discipline of a small team of navigators who refused to look away from a discrepancy most people would have dismissed as noise. The instruments they used to find the anomaly were, in their own way, as much a part of the story as the anomaly itself. The next question was what the spacecraft was actually telling us through the silence. Before the anomaly became famous, before the Pioneer Anomaly even had a name, the spacecraft had already delivered its first scientific bombshell. It happened during the Jupiter encounter, in the days surrounding closest approach on December 3rd, 1973, and it fundamentally changed what scientists believed about the largest planet in our solar system. The discovery was almost accidental. Pioneer 10 had been built to study Jupiter as a planet, in the same sense that we study Mars or Venus as planets, a body with weather and chemistry, and a particular set of physical properties to catalogue. What Pioneer 10 found instead was that Jupiter was not really a planet in the conventional sense at all. Jupiter was something stranger, something almost stellar, something the textbooks of the early 1970s had no proper category for. The clue came from an instrument called the infrared radiometer, a sensor designed to measure the heat radiating from Jupiter's cloud tops. The team operating the radiometer expected to measure the planet's temperature and compare it to the amount of sunlight Jupiter receives. At Jupiter's distance from the Sun, sunlight arrives at roughly 4% the intensity it has at Earth. A passive body absorbing sunlight and re-radiating it as infrared heat should reach a particular equilibrium temperature, and that temperature can be calculated from first principles. For Jupiter, the predicted equilibrium temperature was around 105 Kelvin, roughly minus 168 degrees Celsius. What Pioneer 10 measured was substantially warmer. The planet was emitting nearly twice as much heat as it was receiving from sunlight. The numbers were unambiguous. Jupiter was generating its own internal heat in quantities that no rocky planet, no icy moon, no familiar planetary body had any business producing. The implications were profound. Something deep inside Jupiter, something not powered by sunlight, was producing energy. The leading explanation, which took years to fully develop, was that Jupiter was still slowly contracting under its own gravity, converting gravitational potential energy into heat through a process called Kelvin-Helmholtz contraction. As the planet shrinks by a tiny amount each year, the matter falling inward releases energy, which works its way out through the planet's interior and finally radiates from the cloud tops. Jupiter, in other words, was not yet finished forming. It was still settling, still relaxing into its eventual shape, 4.5 billion years after the solar system condensed from its primordial nebula. The discovery moved Jupiter from being a static, fully formed planet to being something more dynamic, something more alive in a thermodynamic sense, something far closer to the lower end of the stellar mass scale than anyone had previously appreciated. If Jupiter had been about 80 times more massive at formation, it would have ignited hydrogen fusion and become a small star. The Sun would have had a companion. Pioneer 10's measurements confirmed, for the first time with direct data, that Jupiter sits on a continuum that begins with rocky planets and ends with stars, and that our solar system's largest world is closer to the stellar end of that continuum than the planetary end. But the internal heat was only the beginning of what Pioneer 10 found at Jupiter. The magnetic field measurements turned out to be equally shocking. Before the encounter, theoretical models predicted that Jupiter's magnetosphere, the region of space dominated by the planet's magnetic field, would extend a respectable distance into space, perhaps a few million miles. Pioneer 10's magnetometer began detecting Jupiter's magnetic influence at a distance roughly 5 times greater than the most optimistic predictions. The magnetosphere was not just larger than expected, it was the largest coherent structure in the entire solar system. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear larger in our sky than the full moon. The bow shock, the place where the solar wind first encounters Jupiter's magnetic field and is forced to deflect around it, was located far beyond where any model had predicted. The magnetotail, the stretched-out portion of the magnetosphere on Jupiter's downstream side, extended hundreds of millions of miles into space, potentially all the way to the orbit of Saturn under certain solar wind conditions. The planet was not merely big. The volume of space it controlled magnetically was so vast that it dwarfed everything else in the solar system except for the heliosphere itself. The structure of that magnetosphere held its own surprises. The magnetic field lines were tangled, twisted, and reshaped in ways that no theoretical model had produced cleanly. The radiation belts, the trapped populations of high-energy charged particles spiraling along Jupiter's magnetic field lines, contained energies that exceeded the most extreme predictions. The plasma environment around Jupiter's inner moons was rich with sulfur and oxygen ions, hinting at sources nobody had anticipated. Years later, the volcanoes of Io would be discovered, and the source of all that material would become clear. But in 1973, the data simply pointed to something strange happening near Jupiter, something that fit no existing model of how planetary magnetospheres were supposed to work. The reaction within the planetary science community was immediate and almost giddy. For decades, Jupiter had been studied at a distance through telescopes, with all the limitations that implied. Atmospheric absorption blurred the spectra. Distance made fine details impossible to resolve. Theory had filled in the gaps. Pioneer 10 was the first time anyone had ever sampled the planet directly, and the data was forcing a wholesale reconsideration of what Jupiter actually was. Papers poured out of universities. Conferences were organized to discuss the implications. Within a few years, the planetary science community was openly speaking of Jupiter as a substellar object, a body that occupied a category somewhere between planets and stars, with properties that demanded new theoretical frameworks. The textbooks of 1972, which had treated Jupiter as a larger version of a rocky planet with a thick atmosphere, were quietly retired. New textbooks, written in the late 1970s and early 1980s, presented Jupiter as something fundamentally different, a giant gaseous body still in the slow process of stellar-style contraction, generating its own heat, dominating an enormous magnetic volume, and serving as a kind of failed star at the center of its own miniature solar system of moons. This was the first major discovery, and the pattern it established would repeat over and over throughout Pioneer 10's mission. Theoretical predictions, however confident, however carefully reasoned, kept colliding with measurements that did not match. The conventional wisdom, the tidy model of the early 1970s, kept developing new cracks. Jupiter's internal heat was unexpected. Jupiter's magnetosphere was unexpected. The asteroid belt had been emptier than expected. The radiation belts had been more intense than expected. Each surprise was, on its own, manageable. Each could be explained by adjusting a parameter, refining a model, adding a missing physical process. But taken together, they were beginning to suggest something more uncomfortable. The outer solar system was not a place we understood. It was a place we had theorized about from a distance, and our theories were systematically missing pieces. Pioneer 10 was not just gathering data. It was demonstrating, encounter by encounter, how shallow our understanding really was. And the deeper the spacecraft pushed into regions no probe had ever visited, the more frequently the surprises were going to come. The Jupiter discoveries were impressive, but Jupiter, at least, was a place scientists had spent centuries studying through telescopes. What lay beyond Jupiter was territory where even the telescopic guesses ran out, and that was where the truly strange data began to arrive. Pioneer 10 swept past Jupiter at more than 80,000 miles per hour, accelerated by the planet's enormous gravity into a trajectory that would carry it out of the plane of the planets entirely and toward the distant constellation of Taurus. The Jupiter encounter had taken just a few weeks of intense activity, with closest approach and the most dramatic measurements concentrated in a few days. But the journey that followed, the long outbound cruise into the outer solar system, would last for the rest of the spacecraft's operational life. It was during that decades-long cruise that Pioneer 10 made its second great discovery, the one that began to seriously trouble the heliophysicists who had spent their careers modeling the structure of the sun's domain. They had been confident about cosmic rays. They were about to discover they had been wrong. The conventional model of cosmic ray modulation, the dampening effect the heliosphere has on incoming galactic cosmic rays, predicted a very specific behavior. As a spacecraft traveled outward from the sun, it should encounter a steadily increasing flux of cosmic rays, because the shielding effect of the solar wind weakens with distance. Near Earth, the cosmic ray flux varied by a factor of 2 or so over the 11-year solar cycle. Beyond Jupiter, the variation should diminish, and the absolute flux should rise gradually toward the value found in true interstellar space. The expected gradient was something like 10% per astronomical unit, a steady, predictable climb. By the time Pioneer 10 reached the orbit of Saturn at about 10 astronomical units, the cosmic ray flux should have approached the unmodulated galactic value, the level you would find if the sun's solar wind were not present at all. This was the prediction. This was the model. This was what the textbook said would happen. What Pioneer 10 actually measured was nothing like that. The cosmic ray gradient in the outer solar system was much smaller than predicted, perhaps only 1 or 2% per astronomical unit, sometimes even less. The flux of high-energy particles kept rising as the spacecraft moved outward, but it rose far more slowly than any model had suggested. By the time Pioneer 10 was past Saturn, past Uranus, past Neptune, the cosmic ray flux still had not approached the interstellar value. The implication was inescapable. The sun was modulating cosmic rays at distances vastly greater than anyone had believed possible. The heliosphere, the bubble of solar wind that protects the inner solar system from the full force of galactic radiation, extended far beyond the orbits of the planets. The sun was shielding regions of space that nobody had thought it could reach. In the late 1970s and through the 1980s, this single discovery forced heliophysicists to redraw their maps. The original estimate of 50 to 100 astronomical units for the heliopore's distance began to look conservative. New analyses pushed the estimate steadily outward. The heliopause might be at 120 astronomical units, or 150, or even farther. Full extent of the sun's magnetic influence was not a settled number. It was a moving target, and every new piece of Pioneer 10 data pushed it farther into the dark. By the time Voyager 1 finally crossed the heliopause in 2012, the boundary turned out to be at about 121 astronomical units, almost 3 times farther than the most popular 1970s estimates, and exactly in the range that Pioneer 10's cosmic ray measurements had implied. The little probe had been right. The textbooks had been wrong by a factor of nearly 3, but the cosmic ray puzzle was only one layer of the second discovery. Pioneer 10 was also making the first detailed measurements of the solar wind at distances no spacecraft had ever sampled. Eugene Parker's theoretical work in the late 1950s had predicted that the solar wind would spiral outward from the rotating sun in a pattern that came to be called the Parker spiral, with the sun's magnetic field lines wound around the solar system like grooves on a vinyl record. Earth-orbiting and inner-system spacecraft had confirmed the basic geometry. But nobody had ever measured the spiral at distances beyond Saturn, where the field lines were predicted to be nearly perpendicular to the radial direction, almost completely wound around. Pioneer 10 confirmed the broad geometry of Parker's spiral all the way out to its operational limits. The sun's magnetic field really did wind itself into a vast spiral pattern that extended across the entire solar system. What was unexpected was how messy and dynamic that spiral turned out to be. The solar wind at the outer reaches of the heliosphere was not the smooth, steady flow that simple models assumed. It was punctuated by shocks, by interaction regions where fast streams of wind ran into slower ones and compressed the plasma in their path. by sudden discontinuities and turbulent zones where the magnetic field reversed direction abruptly. These structures, called co-rotating interaction regions, formed near the Sun and propagated outward, growing and merging as they traveled, until in the outer heliosphere they could span enormous volumes of space. Pioneer 10 sailed through these structures one after another, year after year, recording the chaotic reality of the solar wind in ways that telescopic observations could never have captured. The Sun was not a quiet broadcaster of plasma. It was a violent, unpredictable, structured emitter whose output rippled outward in vast sheets and shells and spirals, all churning together in the dark. This led, in turn, to a deeper realization about the heliosphere itself. The bubble was not a static container. It breathed. Its boundary moved in and out as the solar cycle waxed and waned, expanding during periods of high solar activity, contracting during quiet years. The cosmic ray flux at any given location depended not only on distance from the Sun, but on the recent history of solar activity, on the structure of co-rotating interaction regions sweeping through the outer heliosphere, on shocks and disturbances that had begun their journey years earlier. The simple model of the early 1970s, in which the heliosphere was a more or less spherical region with a well-defined boundary, gave way to a much more complex picture. The heliosphere was a living, dynamic structure, shaped continuously by the Sun's mood and the local conditions of the surrounding interstellar medium. Predictions about it had to be statistical rather than deterministic. The very idea of a clean, sharp heliopause was beginning to look like a useful approximation rather than a physical reality. The scientific reaction to this second great discovery was different in character from the reaction to the Jupiter findings. The Jupiter discoveries had been exciting, even celebratory. Here was a planet revealed in unprecedented detail, with surprises that opened new fields of research. The heliosphere discoveries were quieter, more unsettling. They did not produce dramatic press conferences or front-page headlines. They produced a slow, accumulating realization within the heliophysics community that the conceptual framework everyone had been working with was inadequate. The Sun's domain was larger than they had thought. Its structure was more complex. Its boundary was less well-defined. And the data driving all of these revisions was coming from a single, tiny spacecraft that had been built in the 1960s with technology that should not have been able to provide measurements this precise this far from Earth. Pioneer 10 was outliving its planners, outlasting its instruments, and overturning theoretical models that had taken decades to construct. The cracks in the conventional picture were widening, and what was emerging through them was a portrait of a solar system far stranger than anyone had been prepared to imagine. The third great discovery did not come from Pioneer 10's most famous instruments. It came from a small ultraviolet photometer that almost did not make the final instrument list, an unassuming device designed to measure faint glows in the deep darkness between the planets. By the late 1970s and through the 1980s, this instrument was returning data that revealed something nobody had expected to find at all. Pioneer 10 was detecting the presence of interstellar matter inside the heliosphere, not at the edge, not just at the heliopause. Throughout the entire outer solar system, a steady, measurable stream of neutral atoms from the interstellar medium was flowing past the spacecraft, slipping through the Sun's magnetic shielding because they carried no electrical charge and were therefore invisible to the solar wind. The galaxy, in a very real sense, was leaking into our own backyard. The physics behind the discovery is elegant. The local interstellar medium, the gas that fills the space between the stars near our Sun, is dominated by hydrogen and helium. Most of it is ionized, stripped of its electrons, and these charged particles cannot easily penetrate the heliosphere because the Sun's magnetic field deflects them. But a small fraction of the interstellar gas remains neutral, atoms that have somehow retained their electrons and therefore carry no charge. Neutral atoms are not deflected by magnetic fields. They flow freely through the heliopause as if it were not there, drifting inward toward the Sun until they encounter solar ultraviolet radiation that eventually strips off their electrons and converts them into the kind of ions the magnetic field can grab. Pioneer 10's photometer detected the resonant scattering of solar Lyman alpha radiation off these neutral hydrogen atoms, and a similar scattering off neutral helium atoms at a different wavelength. By mapping the brightness and direction of these faint glows across the sky, scientists could reconstruct the flow pattern of the interstellar gas streaming through our solar system. The results were extraordinary in their implications. The interstellar wind had a definite direction. The flow was coming from the general direction of the constellation Scorpius and the nearby region near the boundary between Scorpius and Ophiuchus, with a velocity of about 23 kilometers per second relative to the Sun. The temperature of the gas was about 7,000 Kelvin, warmer than the typical cold molecular clouds of the galaxy, but far cooler than ionized regions near hot stars. The density was extremely low, about 1 neutral hydrogen atom per 10 cubic centimeters of space, which sounds like nothing, but actually represents a real, measurable medium. Pioneer 10, simply by drifting outward and observing the diffuse glow of the sky, was characterizing the immediate cosmic environment of the entire solar system. It was telling us, for the first time with direct measurement rather than inference, what kind of galactic neighborhood we lived in. The neighborhood turned out to be a place called the local interstellar cloud, a wisp of warm, partially ionized gas perhaps 30 light-years across, drifting through a much larger and much emptier region called the local bubble. The local bubble itself is thought to have been carved out of the surrounding interstellar medium by supernova explosions millions of years ago, hot stellar deaths that swept up nearby gas and left behind a relatively empty cavity through which our Sun is currently passing. Inside this cavity, smaller and denser clouds like the local interstellar cloud drift around, and our solar system happens to be passing through one of them right now. Pioneer 10's measurements helped pin down the speed and direction of that passage. We are moving through the local interstellar cloud at about 50,000 miles per hour, and we will exit it in roughly 10,000 to 20,000 years, drifting on into the next cloud or back into the empty bubble. The galaxy is not static. Our place in it is not fixed. We are passengers on a slow boat through a textured, structured, dynamic medium that we had barely begun to map before Pioneer 10 started reporting its glow. The helium measurements added another remarkable detail. Helium atoms, being heavier than hydrogen, are less affected by solar radiation pressure. As they stream into the inner solar system, the Sun's gravity actually focuses them into a cone of enhanced density on the downwind side of the Sun, a region scientists came to call the helium focusing cone. Pioneer 10 helped map this cone and revealed it as a real, measurable structure, a kind of gravitational shadow filled with concentrated interstellar helium that the Sun's own gravity had collected. The discovery turned out to have practical applications. Later spacecraft used the helium focusing cone to study the composition of the interstellar medium with much higher precision, but it was Pioneer 10's pioneering measurements that established the cone existed in the first place and gave subsequent missions their roadmap. And then there was the hydrogen wall. As neutral interstellar hydrogen flows into the heliosphere, it interacts with the solar wind in subtle ways. Through a process called charge exchange, where a solar wind proton steals an electron from an interstellar hydrogen atom, the neutral atoms become protons, and the protons become neutrals. This swap creates a pileup of neutral hydrogen just outside the heliopause, in a region of denser, slower atoms that has come to be called the hydrogen wall. Pioneer 10's Lyman alpha measurements provided some of the first hints that such a wall existed, an additional layer of structure at the very edge of the Sun's domain that had not been part of the original theoretical model. The wall is not a literal barrier. It is a region of slightly enhanced density and altered velocity, a piling up of interstellar matter as it pushes against the Sun's outward flowing wind. But its existence reinforced the picture that was now emerging. The heliopause was not a clean boundary at all. It was a complex, multi-layered interface zone with shocks and walls and turbulent regions extending outward into the interstellar medium for distances that depended on how you defined the edges. This was the third discovery, and with it, the pattern finally became impossible to ignore. The asteroid belt had been emptier than expected. Jupiter had been more energetic than expected. The heliosphere had been larger than expected. The cosmic ray modulation had extended farther than expected. The solar wind had been more dynamic than expected. And now, the interstellar medium itself was leaking inside the heliosphere, flowing past the planets, structured into clouds and walls and focusing cones that the theoretical framework of the 1970s had not even suggested might exist. Every single one of these findings pushed in the same direction. The outer solar system was bigger, more complex, more dynamic, and more interpenetrated with its surroundings than scientists had believed. Our cozy little bubble was not actually that cozy. The galaxy was inside us in ways we had not predicted, and our place in the larger interstellar environment was far more intimate, far more exposed, than the textbooks had ever acknowledged. Pioneer 10 was showing us, layer by layer, that we lived in a more porous, more uncertain, more frontier-like region than anyone had appreciated. And the pattern of these discoveries had a disturbing implication. If we had been this wrong about everything we had already measured, what else had we been wrong about? What was the next layer of the picture going to look like when it finally came into focus? The answer, when it came, would be the strangest revelation of all. And it would have nothing to do with hydrogen walls or solar wind. It would have to do with the trajectory of the spacecraft itself. By the mid-1990s, the Pioneer Anomaly had become the kind of problem that quietly drives physicists out of bed in the middle of the night. It was not that the discrepancy was large. The deceleration was so small that, expressed in any units a non-specialist would recognize, it amounted to nothing. It was not that the data was disputed. Anderson's team had spent years scrubbing their measurements, eliminating every conventional source of error they could imagine. It was the combination of features that made the anomaly so deeply strange, so resistant to every attempt at conventional explanation, so suggestive of something fundamentally missing from the textbooks. The more carefully scientists looked, the more impossible the anomaly seemed to be. And the more impossible it seemed, the more seriously physicists began to take the possibility that they were watching new physics happen in real time. The first thing that bothered everyone was the direction. The mysterious deceleration was not pointed in some arbitrary direction. It was pointed almost exactly toward the sun. This was suspicious for a very specific reason. Almost every known force in the solar system, from gravity to solar radiation pressure to the subtle pull of the planets, has a component pointing toward or away from the sun. If you had a measurement error or a modeling oversight, it would very likely show up as a sun-pointing residual, because the sun-pointing direction is where most of the physics lies. So the team had to be especially careful to rule out trivial explanations before claiming a discovery. They modeled the radiation pressure of sunlight on the high-gain antenna. They modeled the gravitational influence of every known body, including hypothetical undiscovered Kuiper belt objects. They modeled the gas leaking from the spacecraft's helium pressurization system. They modeled the differential thermal emission from one side of the spacecraft versus the other. Every one of these effects existed and contributed to the spacecraft's behavior, and every one of them was carefully subtracted from the data. And after every conventional sun-pointing effect was accounted for, the anomaly remained, pointed at the sun, steady, inexplicable. The second feature that puzzled physicists was the constancy of the effect. Most physical forces fall off with distance in predictable ways. Gravity falls off as the inverse square of distance. Sunlight intensity falls off the same way. Even most exotic forces proposed in theoretical physics have characteristic distance dependencies. But the Pioneer Anomaly did not appear to be weakening as the spacecraft moved farther from the sun. The deceleration measured between 20 and 40 astronomical units was, within the uncertainties, the same as the deceleration measured between 40 and 70 astronomical units. This was almost incomprehensible from a theoretical standpoint. If the anomaly was caused by a new long-range force, the force should fall off with distance unless it was extraordinarily exotic. If it was caused by some interaction with the interplanetary medium, that medium should be thinner farther out, and the effect should diminish. The constancy of the deceleration persisting at roughly the same magnitude across vast distances, looked like nothing the standard model of physics had anticipated. It looked uncomfortably like a property of space itself. The third feature was perhaps the most provocative. Pioneer 11, the twin spacecraft launched a year after Pioneer 10, exhibited the same anomalous deceleration. The two probes had followed completely different trajectories. Pioneer 10 had been flung toward the constellation Taurus. Pioneer 11 had used a Jupiter gravity assist to swing past Saturn and then headed out in nearly the opposite direction. Their orbits, their geometries, their thermal environments differed in important ways, yet both showed the same residual acceleration toward the Sun. Two independent spacecraft, observed by independent measurement techniques, refusing to follow the gravitational predictions of Newton and Einstein by the same tiny amount. This was the kind of consistency that turned a curiosity into a discovery. It was the kind of consistency that physicists could not dismiss as a fluke. Through the late 1990s and into the 2000s, theoretical physicists around the world began constructing explanations. Some proposed modifications to general relativity, the most well-established theory of gravity in physics. One family of ideas suggested that at very large distances or very low accelerations, gravity might behave slightly differently than Newton and Einstein had predicted. These modified gravity theories, related to a framework known as modified Newtonian dynamics, or MOND, had originally been proposed to explain the rotation of galaxies without invoking dark matter. Now, theorists wondered whether the Pioneer Anomaly might be a much smaller, more local manifestation of the same underlying physics. Other proposals invoked exotic forms of dark matter, perhaps a halo of slow-moving particles bound to the Sun that exerted a subtle additional gravitational pull. Still others suggested entirely new fundamental forces, fifth forces beyond the four we already knew about, weak enough to have escaped laboratory detection, but strong enough to produce the observed deceleration on extended timescales. A few proposals were even more radical. Some theorists invoked higher dimensional spacetime, suggesting that gravity might leak into extra dimensions in ways that altered its effective strength at large distances. Others proposed that the expansion of the universe itself, normally significant only at intergalactic scales, might somehow be detectable at solar system distances through subtle relativistic effects. A few wondered whether the anomaly might be evidence of a quantum-scale modification of gravity, a hint that the long-sought theory of quantum gravity might leave fingerprints in unexpected places. Each of these ideas had its supporters. Each was published in respectable journals. Each was, in its own way, an admission that conventional physics could not account for what Pioneer 10 was doing. The puzzle deepened when other spacecraft data was examined. Voyager 1 and Voyager 2, which had been launched in 1977 and were also traveling out of the solar system, did not appear to show the same anomalous deceleration with the same clarity. Neither did Galileo, the Jupiter orbiter launched in 1989, nor Cassini, the Saturn mission launched in 1997. This inconsistency was deeply confusing. Why would two Pioneer spacecraft show the anomaly while several other deep space missions did not, or showed it only ambiguously? If the effect were due to new physics, it should affect all spacecraft equally. The fact that it seemed to particularly afflict the Pioneers hinted at something specific to those spacecraft, something about their geometry or their construction that produced an effect masquerading as new physics. But what? Anderson and his colleagues had ruled out the obvious candidates years before. Whatever it was, it had to be subtle. This was the paradox at the heart of the Pioneer Anomaly by the early 2000s. The effect was real, measured by some of the most precise tracking in human history, persistent across decades, consistent between two independent spacecraft. The effect was inexplicable, defying every conventional model of physics that researchers had thrown at it. And yet the effect did not seem to appear cleanly in other missions, suggesting that either the explanation was something specific to the Pioneers, or there was something about the other missions that masked the same underlying phenomenon. Physicists were caught between two uncomfortable possibilities. Either fundamental physics was incomplete in a way the Pioneer data was revealing, or there was a subtle, conventional explanation that had eluded years of investigation. The community could not decide which possibility was more disturbing, and while they debated, Pioneer 10 kept drifting outward into the dark, its signal growing fainter, its deceleration unchanged, carrying its mystery deeper into the silence at the edge of the solar system. The resolution, when it finally came, was both more mundane and more profound than anyone had predicted. It did not arrive with the trumpets that would have accompanied the discovery of new physics. It did not announce a fifth force, a modification of general relativity, or evidence of dark matter in the outer solar system. Instead, it arrived quietly in a 2012 paper published in Physical Review Letters by Slava Turyshev and a small team of collaborators, after nearly a decade of patient, painstaking analysis. The paper was titled, in characteristic understatement, Support for the Thermal Origin of the Pioneer Anomaly. The conclusion was as definitive as such conclusions ever are. The mysterious deceleration that had haunted physicists for 30 years was not evidence of new fundamental physics. It was the spacecraft pushing on itself. To understand the resolution, you have to understand what nobody had been able to model adequately for 3 decades. Pioneer 10 was a tall, thin spacecraft with its high-gain antenna dish pointing back toward Earth, and its electronics compartment mounted just behind the dish. The 4 radioisotope thermoelectric generators sat at the ends of long booms, deliberately extended far from the main body to keep their radiation from interfering with the instruments. Each RTG produced not only electricity, but also waste heat, hundreds of watts of it, far more thermal energy than electrical output. That heat had to go somewhere. It radiated away into space as infrared photons, and those photons, however gentle, carried momentum. Every photon that left the spacecraft pushed it infinitesimally in the opposite direction. The push from any single photon was almost nothing. But the cumulative effect of trillions of photons per second, radiating asymmetrically from a spacecraft with a particular geometry, was exactly the kind of force that could produce a tiny, persistent acceleration along a specific direction. The key word was asymmetrically. If a spacecraft radiates heat uniformly in all directions, the recoil pushes cancel out, and there is no net force. But Pioneer 10 did not radiate uniformly. The electronics compartment behind the dish antenna produced waste heat that was preferentially radiated forward, in the direction the dish was facing, because the back of the dish acted as a partial radiator, while the louvered sides directed heat toward the dish's rear. The dish itself, facing Earth, was effectively the spacecraft's flat side. Heat radiating off the back of the electronics compartment pushed the spacecraft forward toward the dish, which meant pushing it back toward Earth, which meant pushing it back toward the Sun. The geometry was almost perfect for producing exactly the kind of tiny sun-pointing force that Anderson's team had spent decades measuring. And as the RTGs slowly decayed over the years, their thermal output decreased gradually, which meant the anomalous force should have decreased gradually as well. When Turyshev's team examined the data carefully, they found exactly that. The anomaly was not perfectly constant. It was slowly diminishing over time, at a rate consistent with the decay of the plutonium fuel powering the RTGs. This was the resolution. There was no new physics. There was no mysterious force from the edge of the solar system. There was no fifth fundamental interaction lurking in the dark beyond Saturn. The Pioneer Anomaly was the spacecraft's own heat pushing it gently against its trajectory. For 30 years, while the most precise navigators on Earth tried to figure out where the push was coming from. The thermal effect had been considered early on, of course. Anderson's team had estimated it and concluded it was too small to account for the full anomaly, but their estimate had been based on simplified models. What Turyshev's team did differently was to construct a detailed, 3-dimensional thermal map of the entire spacecraft, using recovered engineering telemetry from the original mission, computer-aided design files, and finite element simulations of how heat actually flowed through the spacecraft's structure. When they finally had the geometry right, the numbers fell into place. The thermal recall could account for the full anomaly within the measurement uncertainties without invoking anything exotic at all. The scientific reaction was complicated. There was relief among orthodox physicists who had never been comfortable with the idea that fundamental physics might be wrong in such a specific, peculiar way. There was disappointment among those who had hoped the anomaly might be the door to genuinely new science. There was admiration for the careful, decade-long work that had produced the resolution. And there was, quietly, a much deeper realization that took longer to articulate, but proved more lasting than any individual reaction. The Pioneer Anomaly had been studied with the most precise instruments humans had ever built by some of the most careful navigators in the world for over 3 decades. And the answer, when it finally came, was that we had not fully understood our own spacecraft. Not the universe, not new physics, just the heat radiating off a small piece of machinery we ourselves had built. This is the moment that reframes everything. If the most precisely tracked object in deep space, an artifact of our own engineering with every component documented and every system characterized, could fool the best physicists in the world for 30 years through the subtle redirection of its own waste heat, what does that say about everything else we think we know about the deep dark beyond the planets? Every cosmological measurement, every distance estimate, every characterization of an exoplanet atmosphere or the rotation of a distant galaxy, every conclusion we draw from photons that have traveled billions of light years to reach our detectors, depends on models that are, ultimately, no more certain than the thermal model of Pioneer 10 was in 1990. We learn the universe through the imperfect instruments we make, through the imperfect models we construct, through the imperfect understanding we have of our own measuring apparatus. The Pioneer Anomaly was a stern, multi-decade lesson in epistemic humility. The void is enormous. Our tools are small, and the gap between what we measure and what is actually true is bridged only by careful, patient, honest work that we can never fully verify. But there is a second reframing, and it is even more disquieting. The resolution of the anomaly removed the prospect of new physics, but it did not remove the more fundamental fact about Pioneer 10 itself. The spacecraft is still out there. It still carries its plaque. It is still drifting toward Aldebaran on a trajectory we plotted half a century ago. The deceleration that obsessed physicists for 30 years was, in cosmic terms, almost meaningless. Whether the spacecraft was being pushed by new physics or by its own heat, it was always going to escape the solar system. It was always going to enter interstellar space. It was always going to outlast every civilization on Earth, every monument we have ever built, every memory we will ever record. The resolution of the anomaly does not change any of that. Pioneer 10 is beyond us. It always was. The mystery we spent 3 decades chasing was a small one, a detail of thermal engineering. The larger fact, the truly terrifying fact, is that we sent something into the dark and we cannot follow. We listen for echoes of our own past. We resolve our own confusions. We publish papers and update textbooks. And meanwhile, our first envoy keeps moving, faster than we will ever travel ourselves, into a silence that no resolution will ever break. That is what Pioneer 10 sent back in the end. Not new physics, just a reminder of how alone we are. Pioneer 10's scientific legacy is the kind of legacy that gets quietly absorbed into every textbook and never properly credited. By the time the average student today learns about Jupiter, the heliosphere, the structure of the solar wind, or the boundary between the sun's domain and the interstellar medium, they are learning material that exists in its current form because of measurements a small probe began transmitting in the early 1970s. The probe itself rarely gets named in the introductory chapters. The discoveries are presented as if they had always been understood that way. But almost every modern description of the outer solar system rests on foundations that Pioneer 10 either laid directly or made possible by demonstrating that the old foundations were wrong. The Jupiter revolution alone reshaped an entire subfield of planetary science. Before Pioneer 10, Jupiter was usually described in textbooks as a gas giant, a large planet with a thick atmosphere, distinct from the rocky inner worlds primarily by virtue of being bigger and farther away. After Pioneer 10, Jupiter was reclassified, both pedagogically and scientifically, as a substellar object. The realization that the planet generated its own internal heat through gravitational contraction placed it firmly on the continuum that runs from rocky planets through ice giants, through gas giants, to brown dwarfs, and finally to true stars. The category of brown dwarfs themselves, objects too massive to be planets but too small to ignite hydrogen fusion, emerged as a serious astronomical concept in the years following Pioneer 10's Jupiter encounter, partly because the discovery of Jupiter's energetic interior made the planet-star boundary look much more porous than anyone had previously believed. The first confirmed brown dwarfs were not discovered until the mid-1990s, but the theoretical framework that made them findable owed something to the recognition, made tangible by Pioneer 10's infrared measurements, that gas giants and small stars were members of the same physical family. The heliosphere as a concept was completely rebuilt. The neat textbook picture of the early 1970s, the spherical bubble with a clean termination shock and a clean heliopause at a calculable distance, was replaced over the following decades with something far more textured and unstable. Voyager 1 and Voyager 2, launched in 1977 in a direct continuation of Pioneer's pioneering work, eventually crossed the termination shock and then the heliopause, providing in situ measurements that confirmed in detail what Pioneer 10's earlier data had only implied. The termination shock turned out to be located between 90 and 95 astronomical units, depending on which Voyager crossed it and when. The heliopause itself was at about 121 astronomical units when Voyager 1 crossed it in August 2012. Both of these distances were consistent with the larger heliosphere that Pioneer 10's cosmic ray measurements had been pointing toward for years. And the structure that the Voyagers found, with its multi-layered interface zones, its turbulent flows, its asymmetries shaped by the sun's motion through the interstellar medium, was almost exactly the kind of complex, dynamic boundary that Pioneer 10's data had suggested would be there. Without Pioneer 10, the Voyager missions would have been flying into territory that was much more poorly understood. The maps Pioneer 10 sketched out, however roughly, made the Voyager's deeper exploration possible. The methodological revolution may be the deepest legacy of all. The resolution of the Pioneer Anomaly forced the spacecraft engineering community to take thermal radiation pressure seriously as a routine mission-critical effect that had to be modeled with care for any deep space mission requiring precise navigation. Modern spacecraft are now designed with detailed thermal analyses that explicitly account for the recall from asymmetric heat emission. The Cassini mission to Saturn, the New Horizons mission to Pluto, the Juno mission to Jupiter, and essentially every deep space probe launched after the early 2000s incorporated thermal radiation modeling into their navigation software from the outset. The European Space Agency's Bepi-Colombo mission to Mercury and NASA's Parker Solar probe both rely on thermal modeling techniques whose development was driven, at least in part, by the painful lessons of the Pioneer Anomaly. A discovery that for decades looked like new physics ultimately gave us a much more accurate way to track our spacecraft. The exotic explanations did not survive. The engineering improvements that emerged from the investigation are now permanent fixtures of how we build and operate machines in the outer solar system. Heliophysics, as a recognized scientific discipline, owes much of its modern shape to Pioneer 10 and its immediate successors. The very idea that the sun's influence is a distinct, mappable, dynamic system worthy of study as a whole, rather than a backdrop against which planetary processes unfold, became established largely on the strength of long-duration measurements made by spacecraft like Pioneer 10. Today, NASA operates a heliophysics division that funds dozens of missions, ground-based observatories, and theoretical research programs, all focused on understanding the sun's domain as a coherent astrophysical system. The Interstellar Boundary Explorer, launched in 2008, has spent over a decade mapping the heliosphere's edge by detecting energetic neutral atoms generated at its boundary. The Voyager probes continue to send data from beyond the heliopause as of this recording. The Parker Solar Probe is now diving inside the Sun's corona itself. All of these missions exist within a conceptual framework that Pioneer 10 helped construct, by demonstrating that the heliosphere was a place that could be measured, that it had structure, that it had a boundary worth crossing, and that its outer reaches contained genuine scientific discoveries waiting to be made. There is also a quieter, more uncomfortable shift in scientific culture that Pioneer 10's mission produced. Before the long tail of the Pioneer Anomaly investigation, there was a kind of confidence in solar system physics that bordered on complacency. Gravity in the outer solar system was considered understood. The orbits of planets were considered predictable to almost arbitrary precision. The framework was closed. After 30 years of trying to explain the Pioneer Anomaly, after the slow-motion realization that even our own spacecraft could surprise us in ways that took decades to resolve, the field acquired a different attitude. Theoretical physicists became more willing to take unexplained data seriously, even when it pointed toward inconvenient conclusions. Engineers became more aware of how subtle the interaction between a spacecraft and its environment could be. Navigators became more careful about the assumptions baked into their models. The lesson was not that we had been wrong about a specific thing. The lesson was that being wrong about something for 30 years, in the area of physics most people considered most settled, was always possible. Confidence in deep space measurements became more provisional, more conditional, more genuinely scientific. And the broader cultural impact of Pioneer 10 cannot be reduced to specific papers or methodological improvements. The mission demonstrated something about long-duration exploration that no one had really proven before. A small spacecraft, built with technology of its era, could keep transmitting useful data for over 30 years from distances that grew increasingly hostile and isolating. It could outlive its original mission profile by decades. It could overturn theoretical frameworks. It could carry our message into the dark and keep speaking until its plutonium ran out. Every interstellar mission proposal that has been seriously discussed since, every blueprint for a probe that might someday reach another star, traces its conceptual ancestry back to Pioneer 10 and Pioneer 11. The probes proved that the impossible mission was possible. The textbooks were rewritten. The methodology evolved. And somewhere, still drifting outward, the spacecraft that started it all keeps moving through the cold, carrying its quiet revolution with it. There is a strange intimacy to the Pioneer 10 mission that becomes more visible the longer you sit with what it represents. The spacecraft is not just a scientific instrument. It is not just a piece of Cold War-era engineering or a triumph of the early space age. It is, in a very literal sense, a piece of us. It was built by human hands, tested in human laboratories, launched on a human-conceived trajectory, and sent into the dark with a deliberately chosen message attached to it that says, in the most universal language we could devise, "This is who we are and this is where we lived." Every person who has ever existed since 1972 has lived in a world that has Pioneer 10 in it, even if most of those people have never heard the name. We are all participants in this mission, whether we know it or not, because we are members of the species that did this thing, and the consequences of that act will outlast our entire history. The plaque deserves more thought than most people give it. It was attached to one of the antenna supports by a small group of people working on a tight deadline in 1971, with the explicit intention of being readable by an intelligence completely alien to human experience. Carl Sagan and Frank Drake chose hydrogen's hyperfine transition as the fundamental unit of measurement because it is one of the few physical constants that any technological civilization in the galaxy would necessarily know. They placed a diagram of pulsars around our sun, encoding our cosmic address in a way that could in principle be decoded by any civilization that had mapped its own galaxy. They included drawings of a man and a woman, an act that drew controversy at the time and that has continued to provoke discussion ever since, because the choice of which humans to represent and how to represent them is inevitably a statement about who we believed we were. The plaque is a self-portrait, and like all self-portraits, it reveals as much about the people who created it as about its subject. It captures a particular moment in human history. It captures a particular set of assumptions about ourselves. It captures, perhaps most importantly, the courage to send a message at all to a destination unknown in the hope that someone might one day find it and recognize it as having come from beings who once existed and reached outward. The temporal weight of what we did becomes clearer when you trace the lives of the people involved. Charles Hall, who served as Pioneer 10's project manager and devoted decades of his career to the mission, lived to see his spacecraft's primary mission accomplished, but he died in 1999 while Pioneer 10 was still transmitting. Carl Sagan, who helped design the plaque and championed the cultural significance of sending a message into the cosmos, died in 1996. Many of the original engineers who designed the spacecraft, who soldered the electronics, who calibrated the instruments, who tracked the early Doppler signals, are no longer alive to know how the mission turned out. The spacecraft they built has outlived them. By the time Pioneer 10 sent its last detectable signal in January 2003, more than 3 decades had passed since launch. 2 generations of humans had lived their entire lives during its journey. People had been born, raised, fallen in love, started families, grown old, and died, all while a small probe they almost certainly had never thought about kept silently transmitting from the dark. This is the personal dimension of the mission, and it does not get easier to absorb the longer you consider it. Pioneer 10 was launched in a year when the first email had only just been sent. The personal computer did not yet exist as a consumer product. The internet was an obscure research project linking a few university laboratories. Mobile phones were science fiction. The smartphones in our pockets today are millions of times more capable than the computer that ran Pioneer 10's mission. And yet the spacecraft, built with technology that we would now consider hopelessly primitive, performed flawlessly for 31 years, traveled more than 7 billion miles, and continued working long after the civilization that built it had transformed itself almost beyond recognition. Its persistence is humbling. It says something true and uncomfortable about the relationship between technological sophistication and longevity. The simple, well-engineered, purpose-built thing outlasted the empires of innovation that came after it. There is a lesson there for anyone who is paying attention. There is also a strange democracy to Pioneer 10's existence. The spacecraft does not belong to its engineers, or to NASA, or to the United States, or to any particular living person. It belongs, in some sense, to everyone, because everyone alive today inherits a world in which the act of sending a message to the stars has already been performed. We did not have to do this. We chose to, and the choice was made on behalf of all of us, by a small team of people who decided that humanity should have a representative drifting beyond the solar system. Whether you find that decision arrogant or inspiring depends on your temperament, but it is undeniably ours. The plaque does not say it was launched by a particular country or designed by particular individuals. It says this is the solar system. This is the position of our planet. These are the beings who built me. The framing is collective. The signature is on behalf of the species. This collective ownership extends forward in time as well. Whatever happens to humanity, whatever rises or falls on Earth, whatever new civilizations arise or old ones disappear, Pioneer 10 will continue moving outward. It will be there long after the United States is gone. It will be there long after the English language is no longer spoken by anyone. It will be there long after the human species itself, if we do not survive, has been replaced by whatever comes next, or by nothing at all. The trajectory toward Aldebaran will take roughly 2 million years. To put that timescale in context, modern humans have existed in our current anatomical form for perhaps 300,000 years. Pioneer 10's journey to its first stellar target will be more than 6 times longer than the total existence of our species. The spacecraft is, in effect, immortal on any timescale that human beings can intuitively grasp. It will outlast everything that we mean when we use the word us. This is what it means for humanity on the deepest personal level. We are the first generation of conscious beings on this planet to know with certainty that something we made will outlast us. Cave paintings, monuments, written records, all of these can be destroyed by time and weather and chance. Pioneer 10 cannot be reached. It cannot be recalled. It cannot be damaged by anything we are likely to encounter in the foreseeable future of human history. It will keep going, carrying its plaque and its silence, until eventually its trajectory carries it close enough to another star for some unknown future to reckon with. And that act of permanent reaching, that successful escape from the constraints of our planet's surface, is part of the inheritance every human being now carries. Whether we acknowledge it or not, we are the species that did this. We are the species that managed, however briefly and however imperfectly, to send something true into the dark and to know that it would keep going forever. For all that Pioneer 10 revealed, it left behind a long list of questions that no spacecraft has yet been able to answer. The mission ended on a fundamentally incomplete note. The probe died, in a working sense, before it could cross the heliopause and directly sample interstellar space. Its instruments could measure cosmic rays and neutral atoms streaming inward, but they could not characterize the medium on the other side of the boundary. Its trajectory carried it in a direction roughly opposite to the local interstellar wind, into a region of the heliosphere we still understand only partially. And the broader questions Pioneer 10 raised about the structure of the outer solar system, about the boundaries between our system and the galaxy, about gravity itself at large distances, are still being worked out. The spacecraft pointed at mysteries it could not solve. Solving them is the work of missions we have not yet built. As of this recording, Pioneer 10 is approximately 138 astronomical units from Earth, somewhere out in the direction of the constellation Taurus, drifting at roughly 12 kilometers per second relative to the Sun. We cannot confirm this directly because we have not received a signal from the spacecraft in over 2 decades. The position is calculated by extrapolating its last known trajectory forward in time, assuming the probe has continued moving as the laws of motion predict. Almost certainly it has. The thermal recall that produced the anomalous deceleration has by now diminished to essentially zero, because the RTGs have decayed to the point of producing almost no heat at all. The spacecraft is coasting through deep space, cold, silent, and dark. Its plutonium fuel has long since dropped below the threshold needed to power its transmitter. Even if all of its electronics still functioned, which they almost certainly do not, there is no way to extract a signal from it now. Pioneer 10 has effectively become an inert artifact, an inscribed metal object moving through the void, carrying its plaque and its history into a future no human will witness. This silence raises a question that should bother any astronomer who thinks carefully about it. Pioneer 10 was launched in 1972. Voyager 1 and Voyager 2 followed in 1977. New Horizons launched in 2006 and continues outbound after its Pluto encounter. After New Horizons, there is nothing. There is no spacecraft currently in flight that will reach interstellar space in our lifetimes beyond what is already out there. There is no funded mission to do so. The Voyagers will eventually run out of power, probably sometime in the 2030s, and after that there will be only 4 working interstellar artifacts, all of them silent, all of them moving outward, with no replacements following behind. The Voyagers send back data now from beyond the heliopause, providing the only direct measurements humanity has ever made of true interstellar space. When they go silent, we will lose that capability entirely. The questions Pioneer 10 raised about the structure of the boundary will be answerable only through the Voyagers, until some future mission is built and launched and flies for decades to catch up. The gap is going to be enormous. Several mission concepts have been seriously studied. NASA has commissioned the Johns Hopkins University Applied Physics Laboratory to develop what is called the Interstellar Probe concept, a flagship-class mission designed to reach 400 astronomical units within 50 years. The probe would use a powerful launch vehicle, a Jupiter gravity assist, and possibly a close solar flyby to achieve velocities much higher than any previous deep space mission. It would carry modern instruments capable of characterizing the interstellar medium with a precision Pioneer 10 and the voyagers could never approach. The European Space Agency has studied a similar concept called the Interstellar Heliosphere probe. Even more ambitiously, the Breakthrough Starshot initiative has proposed using ground-based laser arrays to push gram-scale spacecraft toward Alpha Centauri at fractions of the speed of light, potentially reaching the nearest star system within decades rather than millennia. None of these missions are currently funded or scheduled for launch. They exist as concepts, as engineering studies, as ideas in scientific papers. Whether any of them will actually fly remains an open question that depends on political will, budgetary priorities, and technological development that has not yet happened. In the meantime, the questions accumulate. The shape of the heliosphere remains uncertain. Voyager 1 crossed the heliopause in 2012, but Voyager 2 did so at a different distance in 2018, indicating that the boundary is not symmetric. The Interstellar Boundary Explorer, launched in 2008, has been mapping the heliosphere's edge from Earth orbit by detecting energetic neutral atoms produced at the interface, and its data suggests the boundary has a much more complex shape than the simple comet-like model that dominated thinking for decades. The mission that succeeded it, the Interstellar Mapping and Acceleration Probe, has been built to provide a much higher resolution map of the boundary and to characterize the interstellar wind passing through the solar system. But these missions observe the boundary from inside the heliosphere. They cannot tell us what lies beyond it, except indirectly. The hydrogen wall that Pioneer 10 helped reveal is still poorly characterized. The structure of the very local interstellar medium, the cloud through which our sun is currently passing, remains incompletely mapped. We do not know precisely where its edges are, how dense it is in different directions, or what we will encounter when we leave it. There is also the Planet 9 question. Over the past decade, several astronomers have proposed that the orbits of certain distant trans-Neptunian objects show patterns consistent with the gravitational influence of an undiscovered large planet in the outer solar system, possibly between 400 and 800 astronomical units from the Sun. If such a planet exists, it would have been just barely too far away to noticeably affect Pioneer 10's trajectory, but it would represent a major reconfiguration of our understanding of the solar system's outer reaches. Search efforts are ongoing. The Vera Rubin Observatory, which began full operations in the mid-2020s, has been expected to either find Planet 9 or place strong constraints on its existence. The question remains genuinely open. We may live in a solar system with one more major planet than the textbooks currently recognize. We may not. The detection methods have improved dramatically since Pioneer 10's era, but the outer solar system is so vast and so dark that something the size of Neptune could be hiding out there, and we would have only the faintest gravitational hints of its presence. There are deeper questions that no near-term mission can answer. Is the thermal resolution of the Pioneer Anomaly truly complete, or do small residuals remain that might point to subtle new physics? Does gravity really behave the way our equations predict at distances of hundreds of astronomical units? Or are there effects we still have not detected? What is the true composition of the local interstellar medium? And how does it change as our sun moves through different cloud regions over the next thousands of years? What does the cosmic ray spectrum look like just beyond the heliopause, where the modulation by the solar wind ends? Some of these questions will be answered in our lifetimes by missions that already exist. Most of them will not. They will wait patiently for whatever future humanity decides to build the next probe and fling it into the dark. Pioneer 10 opened a door. We have not yet walked through it. There is a particular kind of vertigo that comes from sitting with the timescales involved in Pioneer 10's journey. 2 million years to reach the vicinity of Aldebaran. To make that number mean something, try this. 2 million years ago, on this same planet, our genus had only recently emerged. Homo erectus was wandering the African savanna, learning to control fire, beginning to make stone tools more sophisticated than anything their ancestors had used. Language as we know it did not yet exist. Art did not yet exist. Religion, agriculture, writing, mathematics, science, none of it existed. The entire arc of what we call human history, from the first scratched mark on a cave wall to the launch of the spacecraft itself, fits inside a small fraction of the time Pioneer 10 will spend in transit. By the time the probe reaches its first stellar destination, our species will almost certainly be unrecognizable or transformed beyond recognition or simply gone. And the spacecraft will keep moving, carrying its plaque toward a star that may itself have evolved into something quite different by the time of the encounter, drifting through a galactic environment we have no way of predicting. The journey is so long that the destination, in any meaningful sense, ceases to be a place. It becomes a direction. This temporal vertigo points at something deeper about the relationship between consciousness and the cosmos. We are creatures bounded by short lives, embedded in a universe that operates on timescales we can name but not feel. Our intuitions were shaped by selection pressures that operated over generations, not over geological epochs. We understand seasons because we live through them. We understand the life cycle of a tree because we can watch it happen. But we do not understand, in any visceral sense, what 2 million years means, or what 13.8 billion years means, or what the slow expansion of space across cosmic time really involves. We can write the numbers. We can construct the equations. We can build models that capture the physics. But there is a gap between our ability to know these things and our ability to grasp them, and Pioneer 10's journey lives entirely inside that gap. The mission is real. The spacecraft is real. The trajectory is calculable to within fractions of a mile. And yet what the mission means, in any way that an individual human can hold steady in the mind, is essentially incomprehensible. The act of sending Pioneer 10 was an act of reaching past this gap. We could not travel to the outer solar system ourselves. We almost certainly never will. The energy requirements, the radiation environment, the duration of the trip, all conspire against any meaningful human presence beyond perhaps the orbit of Mars. But we could send a small machine. We could equip it with instruments we designed and built. We could give it a message we composed. We could launch it on a trajectory that no one on Earth could ever follow. And by doing so, we extended our awareness, however thinly, into a region of space that our bodies will never reach. Pioneer 10 became a kind of prosthetic, a way for consciousness to participate in environments that conscious beings cannot physically enter. The data it sent back was not just scientific information, it was a form of presence. For 31 years, a piece of human awareness, mediated through engineering and radio waves, occupied the outer solar system. Now that the signals have stopped, our awareness has been withdrawn back to Earth. But the spacecraft continues. Our presence ended. Our reach did not. This distinction between presence and reach gets at something fundamental about what consciousness is and what it does. We exist as small, fragile, temporary patterns of organized matter on a single planet. We will die, individually and probably also collectively, on timescales that are negligible compared to the universe's own. And yet we have built machines that exceed us. The plaque on Pioneer 10 will be readable, at least in principle, long after every human-made structure on Earth has been ground to dust by weather and tectonic motion. The spacecraft will continue to exist in interstellar space long after our sun has begun its expansion into a red giant 5 billion years from now and engulfed the inner planets. There is a real sense in which Pioneer 10 will outlast the Earth itself. Our reach, expressed through this artifact, exceeds our presence by a margin that defies any comparison to terrestrial things. We made something that participates in cosmic time in a way that we cannot. The melancholy of this is real, but it is not the whole story. There is also a kind of dignity in the act, a recognition of what conscious beings can do even within their narrow temporal windows. The engineers who built Pioneer 10 knew they would not live to see its full journey. They knew with mathematical certainty that their work would persist in environments they would never enter, and they did the work anyway. They poured their careers into a machine that would outlast them, that would carry their species' first message beyond the planets, that would surprise physicists and overturn textbooks, and eventually go silent in a darkness none of them would ever witness. This is not the same as the impulse to build monuments or pyramids or great cathedrals, although it shares some lineage with those impulses. It is something subtler. It is the act of designing for a destination you will never see, of choosing to participate in something whose meaning will only be fully realized long after every participant has died. It is, in a way, the most cosmologically mature thing our species has ever done. The cosmic perspective forces a particular kind of humility, but it also reframes what humility means. We are undeniably small. We are temporary patterns in a vast, mostly empty, mostly unknowable universe. Our individual lives are infinitesimally brief on cosmic timescales. Our species' history is barely visible against the deep time of the galaxy. None of this is in dispute. But the same cosmos that diminishes us is also the cosmos we have begun, however haltingly, to understand. We have measured the age of the universe. We have detected gravitational waves from colliding black holes. We have photographed the event horizon of a supermassive black hole. We have launched a spacecraft toward another star. The same beings who will die within decades have, collectively and over generations, built up an understanding of physical reality that extends from the subatomic to the cosmological. This too is part of the truth about us. The smallness and the reach exist together. They are not contradictory, they are complementary. We are perhaps the smallness reaching, the briefness extending, the fragility insisting on knowing the conditions of its own fragility. Pioneer 10 makes this paradox tangible. The spacecraft is the smallness that reached. It is the fragility that extended. It is the brief, mortal, easily forgotten product of a brief, mortal, easily forgotten civilization. And yet it has succeeded in becoming permanent on a scale that defeats every other artifact we have ever made. Long after we are gone, the probe will still be moving. The plaque will still be there. The trajectory will still be carrying our last message outward. And the silence, far from being a failure, will be exactly what the mission was always going to become. Pioneer 10 was never meant to come back. It was meant to leave, and to keep leaving, and to be, in the end, the kind of thing that conscious beings sometimes do when they have understood enough about their own situation to want to do it anyway. At this exact moment, while you are listening to this, Pioneer 10 is moving through interstellar space at roughly 27,000 miles per hour. It is somewhere in the direction of the constellation Taurus, approximately 138 astronomical units from the Sun, about 13 billion miles away. There is no signal coming from it. There has not been a signal for over 2 decades. Its electronics are almost certainly dead. Its instruments have long since stopped functioning. Its plutonium fuel has decayed to the point of producing only a trickle of heat, not enough to power anything. The spacecraft is, by every meaningful measure, an inert object, and yet it is moving. While you go about your day, while you make decisions and have conversations and worry about the things that fill ordinary human life, the probe continues. It does not need our attention. It does not need our memory. It does not need our recognition. It simply continues, second by second, hour by hour, year by year, drawn outward by the momentum we gave it half a century ago. Picture it for a moment. A small machine, smaller than a car, no taller than a person, drifting through a darkness so vast that the nearest stars are uncountable trillions of miles away. The temperature around it is just a few degrees above absolute zero. The pressure is essentially nothing. The only light reaching it now is starlight, and even that is faint enough that the sun, which once dominated its sky, has been reduced to just another bright point of light among many. The plaque is still attached to one of its antenna struts, slightly eroded by interstellar dust impacts, but still legible to anything that might one day examine it. The instruments that overturned our understanding of Jupiter still sit in their housings. The radiometer that detected the planet's internal heat is still there. The magnetometer that mapped the largest magnetic structure in the solar system is still there. The photometer that revealed the interstellar wind blowing through our backyard is still there. All of them silent, all of them frozen, all of them moving onward with their ship. This is what Pioneer 10 sent back in the deepest sense. Not just the data, not just the discoveries, not just the resolved anomaly and the unresolved questions. It sent back a particular kind of knowledge that nothing else could have provided. It told us, by simply continuing to exist and to function for so long in such a hostile environment, that the boundary between what we are and what the universe is not as fixed as it might seem. Conscious beings on a small planet, equipped with tools they had only just begun to understand, could reach out into the dark and persist there. The reach could outlast the reachers. The artifact could outlive the artisans. The message could survive the messengers. This is a kind of news from the outer solar system that no amount of theoretical work could have substituted for. We had to actually do it to know that it was possible. And once we had done it, the knowledge could not be taken back. The terrifying part of the story is not what most people expect. It is not a monster at the edge of the solar system. It is not new physics that overturns everything. It is not even, in the end, the resolution of the anomaly that turned out to be the spacecraft's own quiet heat. The terrifying part is the silence itself. The fact that we sent something out and it kept going, and now it is beyond us in a way nothing else has ever been beyond us. The fact that we built something that participates in cosmic time and we cannot follow, and we will never know what becomes of it, and the universe is large enough and old enough and patient enough that what becomes of it may not matter to anything for billions of years. The terror is the scale. The terror is the indifference. The terror is the recognition that we exist as small, briefly conscious things in an enormous, mostly unconscious cosmos, and that what we build outlasts us in ways we cannot quite hold steady in the mind. But the terror is also where the wonder lives. If you let yourself feel the full weight of what Pioneer 10 represents, the smallness and the reach together, the silence and the persistence together, the mystery solved and the mysteries remaining together, you also let yourself feel something else. You let yourself feel the strangeness of being a creature capable of doing this, the strangeness of being a creature capable of knowing this, the strangeness of being a small, brief, embedded pattern of matter and energy that has, somehow, looked up at the dark and decided to send something into it. There is no obvious reason any of this should have happened. Atoms could have remained atoms. Molecules could have remained molecules. Life could have stayed at the level of bacteria. Consciousness could have stayed local, embedded only in the immediate concerns of survival. None of these things were necessary. And yet here we are, building machines, sending them outward, listening for their signals, sitting with their silences when the signals stop, and trying to understand what it all means. Pioneer 10 is a piece of that trying. It is one of the most concrete and most lasting expressions our species has ever produced of the impulse to reach beyond ourselves. The probe was built by people who knew they would not see the end of its journey. The plaque was designed by people who knew there was almost no chance anyone would ever read it. The data was analyzed by people who knew that some of the answers might not come for decades. And the legacy is being carried, right now, by everyone alive, whether we know it or not. We inherit a world in which the first interstellar mission has already been launched and is still going. We inherit the discoveries it made and the questions it raised. We inherit the responsibility, if we want to take it up, of continuing the work it began. The next probe to follow Pioneer 10 has not been built. The mission concepts exist. The technology mostly exists. What remains is the choice. Whether we, as a species, decide to keep reaching outward, or whether we let the Pioneer achievements stand as the high water mark of human exploration, depends on decisions we make in the coming decades. Pioneer 10 will keep moving regardless. The question is whether anything else of ours will join it. If this journey through the silence has meant something to you, if sitting with the strangeness of Pioneer 10 and the terrifying beauty of what it represents has given you a fresh way of looking at the night sky, take a moment to like this video, subscribe to the channel, and let us know in the comments what you found most striking. Share it with someone who might want to think about these things too. This is the kind of story that grows in the telling. The more minds we bring to the wonder of what we have already done in space, the more likely we are, collectively, to keep doing it. Somewhere out there, in a darkness no human will ever visit, Pioneer 10 is still moving. It has been moving since before most of us were born. It will be moving long after we are gone. And the fact that we, the small, the brief, the bound, were ever able to launch such a thing into the dark and watch it go is perhaps the most extraordinary thing about being alive on this strange, fragile, lonely planet right now.